Bismillahirrahmanirrahim. We are now looking at the chapter Error Detection and Correction. I will be going through the main concepts. Now, as we know that in a communication medium, when we send the data from the source to the destination, there are chances that this data could go corrupted or could get changed. Things can go wrong and the data can get corrupted. But as we know that one of the main characteristics of successful communication is that the information should not change while going from the sender to the receiver. So for this reason, we need to have mechanisms that will allow us to detect errors and also to correct errors. In this chapter, we will be mainly looking at error detection and not correction. Let's first look at the type of errors. In the first instance, in this example, we have only one bit that has changed from 0 to 1 at the receiver. This means that it is a single bit error because there's only one bit that has gone corrupted. The second type of error is the burst error. In the burst error, you have more than one bits that have gone corrupted. In this case, you have 1, 2, 3, and 4 bits that have gone corrupted. And what is the burst? The burst means the size of this group of bits that have gone corrupted. So in this case, the burst starts here at 0. So you have 1, 2, 3, 4, 5, 6, 7, and 8. So the size of the burst error is 8 bits. So you have single bit error with only one bit getting corrupted, and you have a burst error in which more than one bit have gone corrupted. Now, the most popular way of solving the problem of corrupted data is through the use of redundancy. What do we mean by redundancy? Redundancy means adding more bits. Okay, adding more bits. So we have some bits, we have a message that we want to send. We will be adding some more bits to it and then send it off to the receiver. So these bits that we have added here, these are called the redundant bits. All right, they're called the redundant bits. So these redundant bits are added by the sender and they are removed by the receiver. What is the advantage of adding these bits? These redundant bits will allow us to detect and correct errors. Now the difference between detection and correction. Error detection is far more easier than error correction. Okay, detection is far more easier than correction. Why is that? Because in detection, you only have to say whether an error has happened or not. It may be a single bit error, it may be a burst error, it does not matter. With error detection, you're only concerned with detecting the error. That's all. You only have to say yes or no. But in correction, you have to first detect the error. You have to first say whether an error has happened or not. Then you need to know exactly where the error has happened. And then you need to go and correct that error. So it's more complex than error detection. Now we spoke about redundancy, and redundancy, as we said, means adding more bits. Okay, so you're having the data word and you're adding some bits to it. But these addition of bits is not done in a random manner. You can't just simply take a message, just put some bits in it and send it off. You can't do that. If you add some redundant bits to the message that you're sending, there has to be a relationship between the message and the bits that you're adding. Okay? There has to be a relationship. And then when it goes to the receiving side, the receiver checks this relationship. Right? The receiver will check the relationship and see whether it still exists. If it does, then it means there is no error. If the relationship is not there, it means there is an error. So the sender adds redundant bits through a process that creates a relationship between the redundant bits and the actual data bits. And the receiver will check these relationships, okay, between these two sets of bits to detect errors. Now let's look at the concept of block coding. Let's say we have a message that we want to send. Okay, this message will be divided into a set of blocks. Each of these is k bits in size. Okay, they're all k bits in size. And each one of these is called a data word. Okay, data word. It's pure data. We don't have any redundant bits in this. It's pure data and it's called a data word. Then what do we do next? We take the data word and we add some redundant R bits to it. Okay, we're taking the data word and we're adding R number of redundant bits to it. So then this whole thing is K plus R, which is N. And this new message is now called the code word. Okay, it's called a code word. So code word is K plus R. Data word is K bits. Now, how do we add these R bits? This is all the story. This is what the whole story is about. Okay, how do we add these R bits? Now, in this case, as I mentioned, we're having K bits of data words. If we're having a K bit data word, we can have 2 to the power K valid data words. Okay, just like we saw in the IP address. The IP address is 32 bits in size, so you could have 2 to the power 32 IP addresses. Similarly, you have the size of the data word is K bits, you could have 2 to the power K data words, okay, valid data words. And then we are adding the R bits to them, and this makes the code words, okay, and the code words are N bits, and N, as we know, is K plus R. So the number of code words is 2 to the power N. But there's one important thing that you have to understand. Let's say our data word was 1011011. Okay, let's say this is our data word. And we added to it, let's say, 3 redundant bits to it, let's say. Okay, so this is K and this is R. So this is now an N code word, right? This can only be valid if this sequence of K inside it does not change. So in the N word, you must have the same sequence like this. Only then will it be considered a valid code word. If something goes wrong in this, and if it becomes 11011011, if it becomes like this, it is no longer a valid code word. Okay? So you have to understand that the pattern of the data word inside your code word, it must be the same as the original data word for it to be valid. So this is why, even though we have 2 to the power n code words, only 2 to the power k of them are valid, because we have k 2 to the power k valid data words, right? So only 2 to the power k of these code words are valid. 2 to the power n minus 2 to the power k code words are not valid. Now we are looking at how can we detect these errors using block coding. To be able to detect the errors, there must be 2 conditions that are fulfilled. The first condition is that the receiver has or can find a list of valid code words. Okay? Now we have seen that code words can be valid and they can be invalid. When they arrive at the receiver should be able to say, this is valid, this is not valid. Otherwise, there's no point. If we just send something to the receiver and the receiver doesn't know, the receiver looks at the incoming message and says, is this valid? Is this not valid? It doesn't help, right? So the receiver should have at least a list of valid code words, or the receiver should be able to find out, right? What are the valid code words? And secondly, the original code word has changed to an invalid one. Now, this is another interesting condition. Let's say we have 2 valid code words, and let's say they are 1011, and the second one is 1110. Okay, let's say these 2 are valid code words. Now let's say I have sent this code word and it gets corrupted and it becomes 1001. This 1001 is an invalid code word. We know it. Okay, we know it's invalid. So we will just simply ignore it, or it will be deleted. However, we cannot say the same thing about if this code word gets changed into something else. Okay, and let's see how that is going to happen. So let's see how that happens in here. Right, let's see it again. Oh dear, this thing keeps moving. So again, we said we had the valid code words 1011 and another valid code word 1110. Okay, so these 2 we said are valid code words. Now we said 1011 got sent and we had an error which resulted it into becoming 1001. The receiver looks at this and says that is invalid and will reject it. However, if this 1011 ended up having two errors and became 1110, this is a valid code word, isn't it? So in this case, you had one error and it changed to an invalid code word. But in the second case, you had two errors and it changed from one valid code word to another valid code word. This is problematic. In this case, the receiver cannot say that there has been an error, and the receiver can wrongly consider this as correct when it is in reality it is not correct. Okay, so this is what they mean by here. The original code word has changed to an invalid one. It's very important that the original code word changes to an invalid one. Otherwise, if it changes to another valid code word, we will not be able to detect the error. It is a problem, but it exists. And we have to find different ways of overcoming the problems. Now, there are ways of adding our redundant bits. Okay, and if you see in here, in this example, this is called a simple parity check code method. The data word is 2. The code word is 3. So the R bit is 1 in this case. Okay, so R is equal to 1. Now, how have we put in the R bit? That's an interesting concept. Okay, we are going to consider even parity. Okay, even parity. And what do we mean by even parity? We are going to add bits in such a way that the final result of the number of ones is either 0 or even. What do we mean by that? Look at this data word. The data word is 0, 0. In this case, do we have an odd number of ones here? We don't. So we have 0 ones. So we will add a 0. Because we want the final result to be either an even number of ones or no number of ones. Then look at the second one. You have 0, 1. In this case, we're going to add a 1. Got it? We're going to add a 1 to make it an even number of ones. Then we have 1, 0. Again, we add a 1 to make it an even number of ones. Then we have 1, 1. In this case, we're going to add a 0. All right? We're going to add a 0 so that again the total number of ones is even. So this is called an even parity. We're only adding one R bit. So now you understood there's now a relationship between the R bit and the data word, isn't it? There's a relationship. You're not just adding any random 1 or 0 here. You're checking the number of ones. So you want to maintain them either at 0 or even number of ones. So this is the relationship that we have established between the data word and the redundant bit. So in this case, the sender will encode 01 as 011 and send it to the receiver. The receiver receives 011, check it. It will see that there is an even number of ones. So it will say, this is a valid code word. It will remove this redundant bit. Okay, it will remove it. It will remove this, and then it will take in 0, 1. But it could be possible that this 011 gets corrupted and ends up becoming 1, 1, 1. In this case, the receiver checks the relationship, sees that there is an odd number of ones, and knows that this is invalid, and will discard the code word. But then, as I said, that we have the third example where one valid code word gets changed to another valid code word. In this case, 0, 1, 1 ends up having two errors and getting changed to 0, 0, 0. Now 0, 0, 0 is a valid code word. But then the receiver does not know in this case and incorrectly takes out the data word 0, 0. Okay, so two corrupted bits have now made the error undetectable. So the error detecting code can detect only the type of errors for which it is designed. Other types of errors may remain undetected. In this case, our code was designed to detect single errors. So it will detect single errors correctly, but as soon as we have multiple errors, it cannot detect it correctly. This is what we mean by it. Now in the next video, we will look at Hamming distance and other concepts.